L by L2I dot of T minus 2. Yeah. All I've done is I've replaced T with T minus U, which I can do because of. Now, there's a T minus U here, and there's a T minus U here. Well, let's leave this thing in there. T to come up. And indeed, as we take more tours around the town of classical physics, we'll find this quantity comes up in completely unrelated contexts elsewhere. So we discovered it here, and with a symmetry argument there. So you know we want our equations to look like. We want them to be easier to remember. So we check the T minus U here when in fact it didn't need to. But the check was equivalent. And we got to this quantity T minus U being in two places. Very cool quantity. So let's give it a name. If you come across a quantity in physics and in mathematics and you think it's cool, you generally name it with your surname, and that's what Lagrange did. He called this thing the Lagrangian. Alpha. Right. So let's have a look at how the equations look when we write them in terms of Lagrangian. Well, we've got it there, but let's write it out here. Del O by del Y is equal to d by dt del O by del. That's Lagrange's equations for a conservative. So when we know that all forces in the system are conservative, that all the forces obey being minus the gradient of some potential function, then we can rewrite Lagrange's equations. We can take away this generalized component of force. And I suspect the generalized component of force was the thing that was giving you the most nightmares. In the sense of, out of that algorithm, the step that was the most annoying was computing the generalized component of force. Vector R stars, in the z direction. You know. So we've gotten rid of it. We've gotten rid of it, but only in the case where the forces are conserved. And we can now write this. So now the algorithm, if you like, for computing things in terms of Lagrangian mechanics when all forces are conservative looks like 1. Get the number of positions needed. 2. Write down the generalized coordinates. 3. Get the transformation equations. And that should be this relative transformation equations. 4. Now, we still work out the kinetic energy. But this time, we also work out the potential energy. So once we've worked out the kinetic and potential energy, we can write down the Lagrangian. And once we can write down the Lagrangian, we can write down this equation. Lagrange's equation for a conservative force. And so that's what we do. So our algorithm is roughly the same. The only difference is that instead of computing generalized components of force, we now simply compute a kinetic energy and a potential energy. And then we substitute everything into here. And turn the handle, and out pops the equation of motion. So, very briefly, I'm going to kind of add a bit of an appetizer next. What we will do next time are two things. We'll talk about what a conservative force really is, And then we'll talk about applying the Lagrange equations to systems. And we'll lean heavily on using conservative forces when we have millions and billions and continuous numbers of particles in our systems, rigid bodies and such like. And we'll start being able to use the Lagrange equations to describe things like rocks falling through the air and rotating and so on. What we're going to start doing, we're going to talk about what conservative forces do. So we've seen that a conservative force, we can write the Lagrange equation in this form for a conservative force. We've seen that a conservative force is a force that can be written there. What we're going to look at when we talk about these things, we're going to ask the question, are there other ways to try to but if you do a force, it's sometimes it's conservative. How do you answer? How do you tell me yes, no, and how do you possibly compute this function here? And there are a couple of things that we'll talk about. The first result will be, we'll say, a force is conservative if and only if the work done by that force when I move the system from one place to another is independent of how I move the system. It's only dependent of where I move. So we call that a path-independent force. And in the very beginning of the course, we made that assumption when we were doing our derivation that energy is conserved. We made that assumption. T plus U is conserved. When we move it from one place to another, it's independent of how we move. That's equivalent to saying that a force is conservative. And then we'll throw some ugly mathematics at the board. We'll say that's Stokes' theorem. That's some beautiful mathematics. We'll say, in fact, a force is conservative if and only if, and it's on a simply connected domain, which we'll define, and curl. So we will define all these equivalences, and then we will very quickly be able to compute things like potential energy for a force, and that will enable us to use this formalism of the Lagrange equation. You do have tutorial 8 in the textbook, and you shall meet again Wednesday, another way to catch up with sessions in the lab. For people who haven't checked out the labs 1 and 2, I may have those in other documents related to that. There's no to do that.